been working together, I think, for more than 1 year now. We started looking very generally, discussing like privacy and blockchain, like what it is about, like what are, like we looked at like the whole stack, like zero knowledge, multi-party computation, like a lot of different topics. Then Mario is also co-author of a paper that's basically extends solidity for privacy with privacy annotations, and has a compiler to something that he would talk about today. So, and yeah. Go ahead.
So thanks, Peter, for the introduction. Welcome, everyone, to today's Lunch and Learn. As Peter said, so the Learn portion today will be provided by me. And I'll be talking about data privacy for smart contracts, and more specifically, data privacy for smart contracts using what's called non-interactive zero-knowledge proofs. At a very high level, so how this talk is going to be structured is first I'll give a high-level background info on what zero-knowledge proofs are. I will also talk about a specific form of zero-knowledge proofs, which are called ZK-Snarks, and those are very useful in the blockchain setting. And once we're done with this preliminary stuff, we'll move to a concrete example, which I'll just then play through from start to finish, saying what the scenario is and how we can get this onto the blockchain. And then at the end, some closing remarks, and I'll also quickly talk about the paper Peter mentioned. Yeah, so let's get started. First of all, in zero-knowledge proofs, what is the setting we consider? So we have two parties. One is called the prover, the other is called the verifier. And the prover wants to prove some statement to the verifier. And there are very classic examples of these statements. For instance, we have a Sudoku puzzle, and the prover wants to prove to the verifier that it's actually solvable. Also, there might be a Boolean formula, and the prover wants to prove this is actually satisfiable. And also a very classic example is we have two graphs, and the prover wants to prove that those are actually isomorphic. This setting is not very specific to zero-knowledge proofs. In other interactive proof systems, you would also have a prover and a verifier. So what are the properties a zero-knowledge proof has? First of all, there is completeness. And completeness means that if the statement the prover wants to prove to the verifier is true, then an honest prover, so a prover adhering to the zero-knowledge protocol, will be able to convince an honest verifier that it actually is true. Second, we have soundness. And soundness means that if the statement is not true, a prover cannot cheat the verifier and convince him that it's actually true, except with maybe some small probability, and usually in zero-knowledge proofs, you would have some negligible probability there. So completeness and soundness, I guess some of you will be familiar with those terms. It's also not very specific to zero-knowledge proofs here, just general properties you would encounter also maybe if you have verification. What makes zero-knowledge proof special is obviously the zero-knowledge property. And what the zero-knowledge property says is that if the statement the prover wants to prove to the verifier is true, then the verifier will only learn that the statement is indeed true. So for instance, if we have this Sudoku example, and the prover wants to prove it has a solution or it's solvable, maybe he would do this proof using a concrete solution to this Sudoku puzzle. But because this proof will be zero knowledge, the verifier will in particularly learn nothing about the concrete solution. So yeah, so these three properties are what make up a zero-knowledge proof. Let's talk now about a specific form of zero-knowledge proof, which is called ZK-Snark. So ZK-Snark is quite a mouthful. It's not very obvious what it means just by looking at the acronym. And it stands for zero-knowledge, succinct, non-interactive argument of knowledge. So we can already see here it has what seemingly is 3 more properties than what a normal zero-knowledge proof would have. So let's look at these properties in a bit more detail. So first of all, a ZK-Snark is a zero-knowledge proof that is succinct, which means that no matter how complex the statement is you want to prove, for instance, maybe you have a huge graphs for which you want to prove the isomorphism, or you have a very large program, a very complex program for which you want to prove input-output behavior, you would end up having a proof that is very short. Think of maybe a couple of 100 bytes. Second, it's non-interactive. Non-interactive is only partly true. Of course, there needs to be some interaction. The prover will always need to send the proof to the verifier, but not the interaction in a non-interactive proof is limited. So this means we'll be able to encode the proof in just a single message, send this proof to the verifier, and that will suffice. And lastly, a ZK-Snark is an argument of knowledge. And what this means is that if a prover constructs a proof that is valid and proves the statement, he will not be able to do so without knowing a specific secret, which is usually called the witness. And if we also link this back to our examples in the beginning, for example, the Sudoku puzzle, this would mean that if it's an argument of knowledge, the prover will not be able to construct a proof without knowing a specific solution to the Sudoku puzzle. And therefore, he would be proving actually a stronger statement. He would be proving, I know a specific solution to this Sudoku puzzle, which obviously implies that the Sudoku puzzle is solvable. There's a slight nuance here. So some of you might be able or might be familiar with the term proof of knowledge. And the only distinction to an argument of knowledge is that the property for an argument of knowledge only holds for polynomially bounded provers, so polynomially bounded in whatever the problem complexity is, while a proof of knowledge would hold for any prover, even for unbounded ones. But yeah, that's.
So this is weaker.
This is weaker, exactly. An argument of knowledge is weaker. Yes. So you get this guarantee that the prover knows a specific secret only if he's constrained in his computational power. So yeah, and a proof of knowledge would also be always an argument of knowledge. These specific zero-knowledge proofs, ZK-Snarks, can be used to implement what's called a verifiable computation scheme. And verifiable computation, roughly, the setting is as follows. We again have a prover and a verifier, and we have some program. The prover would go ahead and compute this program, relying maybe on some secret witness. He obtains some output. After he's done so, after he's executed the program P and obtained some output, he would also construct a zero-knowledge proof, a ZK-Snark here, which will attest that, well, I have actually executed this program correctly. He will then go ahead and send the output and the zero-knowledge ZK-Snark proof to the verifier, which then will be able to verify that, okay, this has been computed correctly. And, well, he can store the output or do whatever he wants with the output. Such a verifiable computation scheme, if we think about the blockchain setting, can be used for two things. So first of all, it can be used to ensure data privacy. So how's this? Well, in the blockchain setting, the prover would be someone who wants to interact with a smart contract. And the verifier would essentially be the miner. So every miner would play the role of a verifier. So how do we ensure data privacy? Well, we're already saying there, this program which the prover is executing, it relies on some secret witness. And because ZK-Snark is a zero-knowledge proof, the verifier, so the miners, will not learn anything about this witness. Sorry. Yes.
Secret witness.
Sure. So a secret witness is something that very much depends on the problem instance you're considering. So if we think back to the example statements in the beginning, for example, the Sudoku puzzle, in this case, the secret witness could, for example, be the solution to the Sudoku puzzle. For a Boolean formula, it would be an assignment to the variables that actually shows with this assignment, this formula is satisfiable. And yeah, if we think more about the blockchain setting here, maybe the witness could be the private key. So you're proving that you know the private key such that a ciphertext decrypts under this private key to some value.
So just to repeat this, so if you want a zero-knowledge proof of some existential formula, so exist x such that p of x or something, right? This x might be the witness you're looking for.
Exactly.
So the proof not only just proves that this formula is true, but that the prover found a satisfying x.
Exactly. Exactly. Exactly.
Right.
This is exactly how to think about this.
Right.
So you have an existentially quantified formula, and the x in this case would be the witness. The verifier does not learn anything about the witness, but he will be convinced that the prover actually knows the concrete X.
Constructed an example.
Exactly, exactly. So yeah, this can be used to ensure data privacy. Exactly in this setting. We will see exactly with a concrete P later on in this example. Maybe this will make it more clear because there we'll see a specific example of what such a secret is in a blockchain setting. So yeah, this can be used to ensure data privacy. And it's also an approach to scale blockchains. And this is because of some asymmetric property that ZK-Snarks offer. More specifically, ZK-Snarks are such that when you want to prove something, this might be, so if your program P is very complex, or is a large program, this will take some time to execute this program. And in particular, the more complex this program is, the more complex obviously it is to execute because you have to run through every instruction in the program. On the other hand, so we can basically think of this as slow. On the other side, we have the verification, and the verification is independent of the complexity of the program. So verification, asymptotically speaking, is faster than proving. So how could we use this to scale a blockchain? Well, we have some expensive computation that would normally be done on-chain in a naive setting. We would offload this to some node who does it on-chain, which playing the role of the prover, and afterwards just sending the output and also a zero-knowledge proof to the blockchain and miners verify this proof, and they can just work with whatever the output was, and thus effectively reducing the load on the blockchain. So yeah, two things for which ZK-Snarks in specifically in the blockchain setting can be used for. There is some caveat which should be mentioned here, and this caveat is ZK-Snarks, they require some trusted setup phase. And this trusted setup phase will generate what's in cryptography commonly referred to as a common reference string. And from this common reference string, we would afterwards deduce the keys that we need to generate proofs and also to verify proofs. If this setup phase here is somehow compromised, whoever has the secrets that are used in the setup phase can, in the end, send fake proofs, so proofs that are not actually valid but will be verified as correct. So this is some caveats to keep in mind here.
So if I know the verified secret, I can cheat.
It depends on who does the setup phase, right? So this.
Yeah, of course, of course. Let's say he's a friend, so I learn it, so I can cheat as long as you know the verified.
The keys will not. You shouldn't think about the keys as something that's secret, because the verification key later on, right? Verification happens on chain, will be encoded in the contract itself.
That's public.
Yes, so both keys are public keys. This is not an asymmetric key pair where you have a private key or a secret key and a public key. Yes, this is actually good to clarify. These are just two keys that are needed in the process. But in the generation of this common reference string, there is some randomness being used. And if you know this randomness, you'll be able to fake proofs afterwards. There are some things, I mean, you can, so this setup phase needs to happen once for a certain program for which you want to prove. For a certain P, this would need to happen just once. So you can think maybe what you can do is implement this with secure multi-party computation, but this is yes, we will not touch on this too much here. It's just a caveat that should be kept in mind.
But for the setup phase, it's also true that typically you only need one honest participant, right?
You need one honest participant, yes, but if you don't want to trust this guy, you can maybe use resort to something like secret.
Sure, but like, I mean, at least it's not like you need an honest majority or something.
You don't need an honest majority, and you need it only once, and a single guy suffices that does all this. And what he needs to do is he needs to discard the randomness, so no one can basically get a hold of the randomness afterwards. Yeah. Any more questions at this point? Okay. So let's consider a specific example in the blockchain setting. And the scenario is as follows. We have some cryptographer called Carl here in this example, and he's invented a new hash function. He's very convinced that it's a good hash function. It has some cryptographic properties. And then specifically, he claims that this hash function is a one-way function. Just to recall quickly what a one-way function is, a one-way function is a function such that when given a pre-image, it's very easy to compute the image. But when given an image, it is infeasible to get a corresponding pre-image. So what Carl wants to do is he wants to convince the community of cryptographers that this is a good one-way function. And he promises to reward anyone who can find a pre-image to a hash value he has chosen. So this is the setting we are considering for this example. And in our example, purely for practical reasons, this hash function is SHA-256. Obviously not a new function, but I've chosen this here because it's both supported by the EVM and also by Sokratis, a tool which we'll use later on. So now the clicker is not working anymore. Okay. Sorry? Okay. The button, I guess. Yes. Okay. So I'll do this manually, like the proof here in this example. So first of all, what would be a very naive way of going about implementing such a reward scheme in a blockchain contract? This is a simple contract which has 3 fields. First of all, it's just the prize money. This is whoever is able to submit a pre-image will just get this price here, one ether. It has 2 public fields, 2 additional public fields. One is a target hash. This will just store whatever Carl has chosen as a target hash. So he's allowed to choose some hash. And participants need to find a pre-image to this hash. I've also added here a public member called broken, which just indicates, okay, has a one-way property been broken yet or not? Constructor starting at line 6 is very simple. It would be called by Carl. He would just submit the hash he's chosen, which would initialize the contract target hash field. And then we have a claim price function. Of course, in order for this to somewhat make sense, we would need to check, okay, whoever sends this message has not yet claimed any price money, but for simplicity, I've not done this here. And then in line 12, we would just check, okay, if we apply the SHA-256, does it work? Let's see. Yeah, thanks. And yeah, in line 12, if we apply the SHA-256 to this pre-image that has been submitted to the chain, and we get the target hash, well, the one-way property has been broken. We set broken to true. We reward the sender, and we return true. Yeah, so this would be a very naive attempt of going about this. Obviously, this attempt has a problem. Well, once someone finds a pre-image and submits this to the chain, well, if we submit this publicly to the chain, everyone will learn this pre-image and subsequently can just submit this pre-image themselves and claim the prize money without investing anywhere. So this is obviously not what Carl intended. So what is an approach to address this problem? Well, I have not talked about zero-knowledge proofs for nothing in the beginning. So what we can do is, well, instead of supplying this pre-image in clear text, we just supply a zero-knowledge proof of argument, so that we actually know a certain pre-image, and send this to the chain. Also, in addition, we need to ensure that this is a proof that cannot be replayed by others. For the sake of this example, at least for now, we will assume that it cannot be replayed. At the end, I'll quickly address of how this could be done, implemented. But yeah, for now, we'll assume that it cannot be replayed, and we'll not take care of this in the code itself. So how will we model this solution in this verifiable computation setting? Let's assume there's a participant, Alice, and she's invested some work, and she actually was able to find a pre-image for Carl's hash, which here is denoted as Y. And furthermore, let's consider a program P that takes 2 inputs, W and Z, and it returns one if and only if the SHA-256 of W equals Z. So this is just a function that, given a hash and a pre-image, checks that for SHA-256, the SHA-256 applied to this pre-image equals the hash value. So what Alice does now, in order to claim prize money, she would construct a ZK-Snark, which proves that she knows some W such that PWY outputs to 1. So this is the ZK-Snark she will construct. And the ZK-Snark, she would then supply to the contract on-chain, would verify this proof. And because it's a zero-knowledge proof, well, it would be leaking no information about Alice's pre-image.
Ask a question.
Any question is fine.
So this is a somewhat artificial example, right? Because you could basically make sure that the bounty is only paid once in smart contract.
You could do this, yes, but you cannot. This is somewhat artificial, but you can, for example, could make a fairness argument. That is, so you have two parties. So Carl announces this reward, and several parties start trying to find this pre-image. Sure. And then whoever maybe gets a slight advantage of a tenth a second, or is able, maybe a front-running attack is able to send this earlier to the blockchain, will then be able to claim the reward only, while others already have invested computational power, but not being rewarded. So I think, of course, it's a toy example, but I think it actually makes sense. You can make some fairness.
But there is also another way to screw with this is if you're a miner and somebody submits a transaction to you with the hash, you can submit your transaction or order your transaction with his hash for him and get the price
Exactly.
him as well.
Yes. Yeah. So these issues exist. So it's, of course, it's a toy example, but there are reasonable arguments of why you wanted to do it. And also maybe to address your earlier question, here in this example, the W would be the secret witness.
The pre-image.
The pre-image, exactly. So what is input here is W to the program. So this was the theory of the solution. How do we bring this to the blockchain in practice? And luckily, there exists a nice open source program, which is called Sokratis. And Sokratis is exactly, it's a collection of tools, essentially, to bring these ZK-Snarks to an Ethereum blockchain. And what Sokratis does is it has support for the full pipeline. And the full pipeline means it supports writing a program such as P, such we've seen on the previous slide, in some high-level domain-specific language. And this program P can take public and private arguments. The private arguments will not be leaked by the ZK-Snark that will be constructed from this program. It also supports generating proofs for the programs you're writing in this high-level DSL. And also, very convenient, it has export functionality that gives you a Solidity smart contract, which you can directly deploy on an EVM blockchain, which will verify proofs for a certain program. Let's look at in more detail of what the workflow of Sokratis is. So in the beginning, you start with some high-level code, which will be written in Sokratis domain-specific language. And for our simple example here, we'll see the specific code in, I think, on the next slide. So you start with this, and what happens first, you would compile this code into an intermediate representation, which is here termed flattened code. And the flattened code is basically just a constraint system. So it has two things. It has assignments of variables, and it has assertions. And this intermediate representation is chosen because ZK-Snarks expect a certain representation of your program. And this flattened code here very easily maps to this representation. So once you have this flattened code, you can very easily go ahead and construct ZK-Snarks. Then you would run the setup. And this is the trusted setup I referred to earlier in my talk. Exactly. And so this would generate us two keys. One key for verifying the proofs for this high-level code we've written initially, and one for constructing proofs. Once we have these keys, we can take the verification key and go ahead and construct this or export Okay, we can go ahead and construct a verification contract. And just this also links to what we already discussed before. This verification key is needed for this verification smart contract, so it will be encoded in the contract. It is a public key. So public meaning everyone is allowed to know this key. And yeah, so this is basically the verification pipeline. And then on the other side, if you want to generate a proof, we've already said ZK-Snarks are a proof of argument. So what you need in order to be able to construct a specific proof, you need a witness. So you will go ahead and construct a witness. For this, you need to know the private information, for example, the pre-image. Yes, in our running example that calls hash function. And once you've computed the witness, you can go ahead and generate the proof using the public key. So this is a high-level workflow of Sokratis. So let's look at how our program P for our running example would be written in Sokratis domain-specific language. So we have one function. Sokratis, however, supports multiple functions, so you can have functions calls, and all these functions are statically scoped. Our main function here takes 6 arguments. So the first 4 arguments, A, B, C, D, are all marked as private, which means any ZK-Snark you construct will not leak any information about any of these values. And in our example here, we use A, B, C, and D to encode our pre-image. And why do we have to use 4 arguments to encode a single pre-image? This is due to some technical details of Sokratis. So Sokratis operates on a specific, in a prime field, and it can only encode integers up to a certain number. So we have to split somehow. So this is due to a technical detail, essentially. The same applies to the target hash here. So we need to split this for the same exact reason. But note that here the target hash, so which will be the hash that is chosen by Carl, is not marked as private. So we can leak about the target hash, but the pre-image should be kept secret. And then in line 2, we will just compute the SHA-256 of our pre-image. And in line 4 and 5, we will compare that it actually matches our target hash. And these double equal sign here should just be read as an assertion. So this will assert that the first element in this array we get from our SHA-256 call matches the first portion of the target hash, and similarly the second portion of what we receive from our SHA-256 call matches the second portion of the target hash. And if none of these assertions fail, this program would return 1. So this means we return 1 if and only if the SHA-256 of this pre-image matches the target hash. So I will now go ahead and just quickly play through this workflow on our example program, just to see really, okay, how is Sokratis used in practice?
You can zoom a bit.
Is this possible to zoom somehow?
I guess it's a terminal.
Huh?
Like on your laptop. Yeah, you would do it.
Zoom in. I've never zoomed. Wait, let's see.
What terminal do you use?
It's just normal back.
Just go to view to the
View,
left.
yeah, we'll try view.
Yeah,
zoom in.
six.
Control plus plus.
Okay. Let me know when it's
I
sufficiently.
think that's fine.
Okay, fine.
That's good.
Okay, so I'm here in a folder which has two elements. The first one is not really relevant. It's just that I can later on generate this witness, and the first one actually has the code, the Sokratis code, which I just presented on the slide. So first thing we will do is it possible to read?
Yeah.
So we will first go ahead and compile this code into the intermediate representation. So this will take a couple of seconds, and you should soon see here just constraints popping up. Looks like gibberish, but that is what it's doing essentially. So this takes a couple of seconds to get this intermediate representation of the constraint system. And
looks very zero knowledge.
it is, well, it might be just obfuscated. Yeah, so yeah, this was the first step. The second step would be to run a setup phase. And maybe, so we can see now we have the output, which is basically this constraint system. So now let's run the setup phase. This will also take a couple of seconds. Takes as input the constraint system, and will produce us 2 keys, 1 verification key and 1 key for constructing proofs.
The setup uses the flattened code.
It does use the flattened code.
It
Yeah.
does.
Yes.
Is it like can be public as well.
Both are public, yes. Because, so for instance, if you think back to the example of this pre-image, obviously anyone should be able to construct a proof that they found a pre-image. So both are public.
So it's sort of like analogy with a generator and for electric curve.
What exactly is an analogy?
Do you know electric curve?
Yeah, this is all based on elliptic curve.
Yes, so this is basically generator and this special number.
Yes,
something like
yes,
that.
yes. Okay, and then now that we have the two keys, we can export our verifier, which is quick, and you can see some Solidity code has popped up here, and you can here see the verify transaction function, which we then can call on a proof. The proof is A, B, C. Those are points on an elliptic curve. And this function will precisely return true to us if it's a correct proof and false if it's an incorrect proof. So now we can generate our witness. So the first three arguments here, I have obviously an example because I would not be able to come up with a pre-image of a given SHA-256 on the fly. So let me see, this will be a bit tough. So this is what the pre-image will be. It's basically 1, 2, 3, 4, 5, 6, 7, 8, prepended with all zeros. And so the hash, I have to look up now. This works. So remember that the first four arguments,
You need a space, right?
yes, I forgot the space somewhere.
248. Yeah, you're there. Yeah.
Okay.
There.
Perfect. Okay. Oh yeah, I've misspelled it. Let's compute this. Okay, let's hope this works. Yes, looks good. And then in the end, we should be able to verify. So the witness, what this actually is in this case, we have our intermediate representation of the flattened code. And the witness is now an assignment to all the variables in this code, which corresponds to executing the program P. And so luckily, this has all worked now because we can see here on the very bottom, the value that is assigned to the output is 1, which means all the assertions in the program have worked. And yeah, so meaning we found a pre-image. And then as a last step, we can generate a proof. And this will output us here a JSON. See? It's a bit tough to see now because it's scaled up, but essentially this is a JSON containing the proof and the public arguments. And we can see, I showed you this verify transaction function earlier on, which expects A, B, and C. And these are exactly the A, B, and C you have to input there. So this is your proof. And as you can see, it's a reasonably short proof. So it's not something huge. It's not many megabytes which you have to supply. OK, so essentially, this was the full pipeline which we would do in Sokratis for our example. And to wrap up this example, just let's see how the initial break my hash contract would now look like. Not much will change, actually. So we still have our price money field. The target hash is now split in two. I've done this for convenience because that's what Sokratis expects as a public input for the program. And broken is exactly the same. The field that's added here is this verifier, which is the contract I showed you on the terminal, which has this verify transaction function to which we can input a proof. The constructor also hasn't changed much, so it will initialize the target hash, and it will also initialize the verifier. Then we have our claim price function, and the arguments it gets now is no longer the pre-image, it is a proof, so A, B, and C. And similarly, we would first check, okay, this message sender has not yet claimed any price money. We would build our public input, and the public input are exactly, so it's the target hash, and the last element here, which you can see, is this 1. So the proof would verify that, okay, actually, this has executed to 1. And so we call the verify transaction function on the proof and this public input, and we require that it returns true. So, I mean, I guess you're all familiar more or less with Solidity. So if this require here fails, the transaction will be reverted, and in particular, the sender will not get any prize money here in line 27. So yeah, not too much changes. Okay, so this wraps up the example, and let me give some remarks and some final takeaways. So first of all, this was a toy example, and we have some issues. So I mentioned replay attacks in the beginning, and there are certain measures you can take to prevent replay attacks. For instance, what you can do is that you, in addition to proving that you know a pre-image to the target hash, you also prove that you know the private key to whoever gets the money. So this would mean that a different account, they might be able maybe to replay this, but if we also check that an account receives prize money only once, then there's nothing. So at least no other account can claim prize money for themselves. There are also maybe Sybil attacks. So if you have a pre-image, you could construct maybe another account and then just do the proof again because you know the pre-image, and then you would just prove that you now know the private key to a different account. And I have to say, I don't think this can be prevented purely on-chain. So maybe some off-chain ID check enrollment phase would need to take place in order to get rid of this. Anyhow, the ZK-Snarks here have shown us how we can reasonably come up with a scheme that allows rewarding multiple participants and not just one. And in particular, also, if we prevent this replaying by proving that we know the private key to whoever gets the message sender, it will also counter this attack you have mentioned previously. There is a fairly general formula of how we can bring data privacy to the blockchain. And this is as follows. So if there should be private data on-chain, we haven't seen this in the example, but this is also a use case maybe when we have a wallet and we want to store the balances on-chain. We would simply store them encrypted on-chain. If we want to compute on this data, we're doing this off-chain using the secrets we know. And after we've done so, we send the updated ciphertext and a zero-knowledge proof that attests that we've done the computation correctly to chain. And this proof obviously then will be verified on chain. And yeah, these ZK-Snarks are fairly widely applicable, and in particular, Zero Cash is using this, or Zcash is using this for providing anonymous transactions on the blockchain. Some final remarks on some research we are doing at the SRI lab, and Peter has already hinted at this in the beginning. So first of all, if we want, so we've seen an example now, but this was a fairly small example. If we want to do this for general, maybe more complex contracts, you would have several functions with more complex logic, more complex than just proving a single equality. Then this can get, doing this manually, like I've done now in the terminal, and then transforming the on-chain contracts, this can get tedious quite quickly. It can also become a bit error prone because the privacy guarantees you get are not very immediate. So you have to look at the code, you see some verification calls here and there, but it's not obvious. And also, if you do this manually, you're ending up writing a Solidity contract as shown before, where you just have a verify call. It calls some verifier, but you don't know what the logic is that is actually verified. Right? You can't see this from just looking at this contract. The logic will be scattered between Sokratis, DSL, and on-chain contract. And so we are addressing this by the blockchain privacy language, BPL. And BPL is similar to Solidity, a high-level language, but it additionally is aimed at constructing privacy-preserving smart contracts. And just on a very high level, so what BPL offers is, if you have variables or function arguments, in addition to just them having a type as you're used to normally, they also have a data type. They also can have a privacy type. So for instance, we have a secret here defined, and it is of data type uint, and we assign it a privacy type owner, which means secret on-chain will be private to the owner. BPL has a type system which checks that whatever contracts are written are actually realizable using these zero-knowledge proofs, and which also is aimed at preventing unintended leaks of the secret. For example, if you try after defining the secret here, if you want to write this to public storage, this will be something that was, without explicitly revealing this will be something that will be captured by our type system. And lastly, so you can write contracts in BPL, and we have a compiler which will then compile this to normal Solidity code, which you can deploy on an EVM blockchain. So yeah, this is just some high-level view on research we've been doing at the SRI lab. And yeah, with this quote, which presumably has served as inspiration for the inventors of Sokratis, I'm closing my talk and happy to take questions.